In this first problem, we have three vectors we'd like to add together to form a resultant. The vectors in part A are force vectors having units of pounds. The vectors in part B are position vectors having units of millimeters. You should pause the solution here and try to work through these problems yourself. When you're ready, resume playing to see one solution to the problem. We stated in our discussion that the order in which vectors are added together is irrelevant. We can choose any order we like. In this case, in both parts A and B, we have one vector which is horizontal and one vector which is vertical. So it seems like a good idea to start with those two because we'll immediately get a right triangle to start with. In part A, we have an 80-pound force here, and we'll add tail to head. So our first addition will involve the 80-pound and 60-pound addition. And that will produce an intermediate resultant here. We'll call this Q, and we'll call the angle that it makes with the horizontal theta. Now, since this is just a right triangle, we know that the magnitude is the square root of the sum of the squares, and that turns out to be equal to 100 pounds. Theta can be found in a number of different ways. Among other ways, it's the arctangent of 60 over 80, and that happens to give us 36.9 degrees. We can now take the next step of adding the 40-pound vector onto Q. We further know the angle between these two vectors, since 40 pounds is given as making a 45-degree angle with the horizontal, and we know that the 100-pound vector makes a 36.9 degree angle with the horizontal, so we end up with an angle here between them that's 45 degrees plus 36.9 degrees, which is equal to 81.9 degrees. Our final resultant is this vector, and now we can use the law of cosines to say that the magnitude r is the square root of 100 squared plus 40 squared minus 2 times 100 times 40 times the cosine of 81.9 degrees. And that number turns out to be 102.3 pounds. To complete the orientation, let's define an angle phi here between the 100-pound force and the resultant. And now we'll use our law of sines to say that the sine of 81.9 degrees over the magnitude of r, which is 102.3 pounds, is equal to the sine of phi over 40 pounds. This gives us the sine of phi is equal to 0.387, and that produces an angle phi from the arcsine of 0.387 of 22.8 degrees. Adding that 22.8 degrees to the 36.9 degrees we got earlier gives us an end result that r is equal to 102.3 pounds at 59.6 degrees measured off the horizontal. You should now pause here and try part B before proceeding further. In part B, we once again have a situation where we have one vector that's vertical and one that's horizontal, and so it seems easiest to begin with those two. We have an 8 millimeter displacement or position vector which moves to the left, and we have another 8 millimeter vector that points down. And once again, since this is already a right triangle, we can find magnitude and direction quite easily. We call this again Q, and we'll again call theta the angle that the intermediate resultant makes with the horizontal. In this case, theta is making an angle with the horizontal that points off to the left. Once again, our magnitude Q is just the square root of the sum of the squares, and that's particularly simple in this case. It ends up being equal to 11.31 millimeters. And the angle theta we could find is the arctangent of opposite over adjacent, which is just the arctangent of 1, and that's 45 degrees. For the second step, we have our intermediate resultant Q of 11.31 millimeters, and we're now adding the third vector, which is 15 millimeters, that makes a 30-degree angle from the horizontal, and that gives us a net result here of 45 plus 30 degrees, or 75 degrees. And since we know Q and 15, and we have the angle in between them, we can once again use the law of cosines to get our final resultant here. The magnitude R is the square root of 15 squared plus 11.31 squared minus 2 times 15 times 11.31 times the cosine of 75 degrees, and that turns out to be equal to 16.28 millimeters. Once again, we can define the angle phi between the intermediate resultant Q and our final resultant, and we can say that using the law of sines, that the sine of 75 degrees over 16.28, which is the magnitude of R, millimeters, is equal to the sine of phi over 15 millimeters. And if we calculate that out, we get that the sine of phi is equal to 0.89, and that phi is equal to 62.9 degrees. Now, if we wish to do so, we could reference the final position vector off the horizontal axis pointing off to the right. We could do that in a couple different ways. We could first go all the way around in a counterclockwise direction, which would involve adding 180 degrees plus 45 degrees plus phi is 62.9 degrees, and that result would give us that vector R is equal to 16.28 millimeters at 287.9 degrees, measured from the horizontal axis in a counterclockwise direction. But that's a rather large angle, so we could alternatively say that it's 16.28 millimeters at 72.1 degrees, measured in a clockwise fashion from horizontal. For our second example, we would like to determine the smallest force F1 such that the resultant of the three forces F1, F2, and F3 is vertical, and we would like the angle at which F1 should be applied. Again, you should pause here and try the solution yourself, then when you're ready, resume playing to see one solution. Unlike the previous problem, we don't know all the force magnitudes and directions to start. We have one force that has neither known magnitude nor known direction. We do, on the other hand, know where our resultant is supposed to point. It's supposed to point straight up. In this case, beginning with a general force polygon can be a good place to start because it informs the choices we're likely to make for F1. Since the forces F2 and F3 have both known magnitude and known direction, we'll begin by sketching those. F2 is the larger of the two known forces. We'll sketch that first. And that makes an angle of 45 degrees from the horizontal. And then we'll add to that F3, which is a smaller force that makes a shallower angle with the horizontal. And once again, since the angle between the 200-pound force and horizontal is 45 degrees, and the angle that the 100-pound force makes with the horizontal is 30 degrees, this angle ends up being 75 degrees. From here, we can sketch several candidates for F3, knowing that the resultant has to get back to the vertical direction. And what we can see from that is that the smallest value that the force F1 can have will be the one that meets the intended direction at a 90-degree angle. So this gives us half the problem solution right away. We know that alpha must be equal to 90 degrees. It remains to find the magnitude of F1, and that's straightforward enough as follows. First, we can form an intermediate resultant Q. We can find the magnitude of Q from the law of cosines, and we can find this angle theta using the law of sines. We might also note that we could find the angle phi here from the difference between 90 degrees and the sum of 45 degrees plus theta. Because we're dealing with a right triangle, we could then find F1 from Q sine of phi. So one procedure here is to use our law of cosines and law of sines to find the intermediate resultant Q and its orientation through angle theta, and then use the properties of the right triangle that results from knowing that F1 has to meet the resultant direction at 90 degrees to find F1 as Q sine phi. Carrying out these details, we have Q is equal to the square root of 200 squared plus 100 squared minus 2 times 200 times 100 cosine of 75 degrees, and that number turns out to be equal to 199.1 pounds. We then also have the sine of theta over 100 pounds has to equal the sine of 75 degrees over the magnitude of Q, which is 199.1 pounds. And rearranging this, we end up with sine of theta is equal to 0.485, and theta is equal to 29 degrees. Finally, we have that phi is equal to 90 minus the quantity 45 plus 29. That ends up giving us 16 degrees, and F1 is equal to Q sine phi, so it's 199.1 sine of 16 degrees pounds, and that ends up being 54.8 pounds. So our final result is that F1 is equal to 54.8 pounds at 90 degrees measured counterclockwise off the vertical.